Today we're going to talk all about nuclear energy, fusion, and fission. There are nuclear power plants all over the world that we use to generate energy. We use uranium to generate energy, and this powers a lot of countries' electricity supplies. But what kind of energy are we harnessing? Let's begin with nuclear energy. Einstein predicted that if the energy of a body changes by an amount E, its mass changes by an amount m, and there is the equation E equals mc squared, where c is the speed of light. What he's telling us is if there's a certain mass and it goes through a certain reaction and the mass decreases, let's say the mass decreases by 1 gram, then the energy released by that is going to be 1 gram times the speed of light to the power of squared. What he's implying here is that every single gram of mass is an extremely concentrated store of energy, because obviously c squared is a very, very high value. The implication is that any reaction in which there is a decrease of mass, called a mass defect, is a source of energy. The energy and mass changes in physical and chemical changes are very small. Those in some nuclear reactions like radioactive decay, which is what fusion and fission makes use of, is millions of times greater. So the type of nuclear reaction that we make use of right now in these nuclear power plants is fission. In fission, we use something called uranium. Uranium is a heavy metal and it has a bunch of different isotopes, but the one that we use is uranium-235, and therefore it's the most important one that you should remember. Some atoms of this isotope uranium-235 decay quite naturally, and when they decay, they become more stable, and in order to achieve this, they emit a neutron. But the thing is, when a neutron collides with a nucleus of uranium, because this uranium nucleus is already quite unstable, it can actually break, and this is called the fission of the nucleus. When it breaks into two nearly equal radioactive nuclei, so almost of the same size, and it's often barium and krypton, but obviously different nuclei can also result. And not only is barium and krypton produced, there is also around 2 to 3 more neutrons that get produced when this nucleus breaks down. So this means that as the uranium breaks, because it got hit by a neutron, it emits even more neutrons. And as you might expect, these neutrons might also collide with the other nuclei next to them, who will then break down as well. And then they're going to make the other ones break down as well. And it's going to get bigger and bigger and bigger. And this is what we call a chain reaction. So in a chain reaction, this is what happens. A neutron hits a uranium-235, and then it breaks into two, and there's fission fragments, and there's also these green fission neutrons, and the neutrons will hit the other atoms next to it. In a chain reaction, the mass defect is large, and it mostly appears as kinetic energy of the fission fragments, and these fly apart at great speed, colliding with the surrounding atoms, and it raises the energy of the surrounding atoms as well. So the particles, they have a higher kinetic energy and they're colliding with each other more often and they're moving faster. This means that their thermodynamic temperature will also increase. This is heat energy, and you can harness that by using steam, and you can also use that steam to turn a turbine, and that's basically how a nuclear reactor works. If the fission neutrons split other uranium-235 nuclei, a chain reaction is set up. And this means that it is self-sustaining. So you don't need to keep applying more neutrons to sustain this reaction. This reaction is going to get bigger and bigger by itself because it already emits neutrons in the reaction. Some fission neutrons are lost by escaping from the surface of the uranium before this happens. The ratio to those causing fission to those escaping increases as the mass of uranium-235 increases. So the mass of uranium-235 must exceed a certain critical value to sustain the chain reaction by itself. So when you have a higher mass, you have more volume of the uranium in proportion to the lost neutrons, and therefore you can sustain the reaction by yourself. So let's take a short look at the nuclear reactor in which these reactions take place. First thing that you can realize is that there's a concrete shield all around what where the reaction happens. And this light bulb shaped thing is where the reaction is happening. So the concrete shield is obviously going to absorb the radiation from this. You'd not only have neutrons that are flying about, you can also have things like gamma rays. And when you get hit by a lot of gamma rays, it can cause cancer, for instance. There are villages around nuclear reactors. There are people who work in nuclear reactors, and hence we need the concrete shield. In the light bulb thing, we see the green uranium rods, and that's exactly where the reaction takes place. However, there are rods of boron as well as graphite, and this is going to help regulate the rate of the reaction so that it doesn't get out of hand and cause a nuclear bomb. And you can see that there is this thing called a heat exchanger, so you can put cold water into the light bulb thing, and this is going to heat up the water into steam, because as we said, the energy that is released, which E equals mc squared, it's actually mostly present as heat energy. This is going to heat up the water into cold gas, and this is going to be steam, and obviously the steam can turn a turbine, and this is kind of the same as a lot of other types of energy and how they are harnessed. We usually use steam to turn a turbine. So this chain reaction occurs at a steady rate, and this is controlled by inserting or withdrawing neutron absorbing control rods of boron among the uranium rods. So the more boron you have, the more neutrons are absorbed. And if you realize that the reaction is really big and there are a lot of nuclei that are present in the reaction, then you want to put in more boron rods so that you can have less neutrons. So that explains the boron. What about the graphite core? Well, the graphite core is called the moderator. The thing that the graphite does is it slows down the neutrons, and basically the fission occurs much more readily with slow neutrons than fast neutrons. So you want to make sure that these fission effects are happening more readily at a higher proportion of the total uranium, and therefore you're slowing down the neutrons, sorry. So usually we also have carbon dioxide gas being pumped through the core as a coolant, as an alternative to water being pumped through. And if you don't control the rate of uranium going through fission, it can actually become a bomb. And this is kind of like an atomic bomb. In an atomic bomb, an increasingly uncontrolled chain reaction occurs when two pieces of uranium-235 come together and exceed the critical mass. Once there is more than the critical mass, then that means that there is a chain reaction and it sustains itself. And as you can see, there are like 2 neutrons that are produced every single one fission. So basically, one atom produces 2 neutrons. That means that 2 atoms can basically go through fission. That's going to make 4 neutrons, and then 8 neutrons, 16 neutrons, etc., etc. This is going to increase at an exponential rate and increasingly emit an exponential amount of energy in a very, very short amount of time. And this is what makes an atomic bomb. So the last thing we're going to talk about today is fusion. Fusion is the polar opposite of fission. Whereas fission, you have very, very big nuclei that are unstable, like uranium-235, and so breaking it to pieces makes the nucleus more stable. For fission, you have small nuclei that are unstable, and joining them together makes them more stable. If light nuclei join together to make heavier ones, this can also lead to a loss of mass, and therefore, as a result, the release of energy. So fusion can only occur if the reacting nuclei have enough energy to overcome their mutual electrostatic repulsion. Because in fusion, it's nuclei that are joining together, whereas in fission, all we need is a neutron that's hitting the nucleus. So a neutron is neutral, therefore it doesn't experience any electrostatic repulsion. However, when 2 nuclei come together, both these nuclei are positive, and therefore the repulsive forces are going to be horrendous because they're going to be so close together. So if there is enough energy, enough kinetic energy to repel it, that's when it can happen. Usually this means heat. You need a lot of heat, and then these nuclei are going to be traveling at extremely fast velocities. So at these high velocities, even though the repulsive force is very strong, they cannot decelerate these nuclei enough to make them stop and turn around. Instead, they will collide with each other, and then fusion will happen. So if fusion occurs, the energy released is enough to keep the reaction going because the energy released is immense and it's going to heat itself up. So really what matters is the first step. If the first step happens, then the next steps are going to happen, and that's all good and fine. And so the source of the sun's energy is actually nuclear fusion. In the sun, basically, there are two isotopes of hydrogen that they add up and they make helium. And this is, for instance, deuterium and tritium, which are isotopes of hydrogen. Now, there have been many efforts to create fusion on Earth so that we can kind of harness energy in this way as well. It's really nice because there are less radioactive fallouts. I think there's actually no radioactive fallouts, and even fusion has a lot of radioactive decay, and that's extremely bad, obviously. As said, the barium krypton that's made in uranium fission is radioactive, and this is radioactive waste, which can be very bad for the environment. For fusion, that doesn't happen at all. Helium is completely fine and good. So there have been efforts to make it, but this means that we need the temperature of the sun, or well, really, really high temperatures in order to sustain this reaction, and we simply don't have the sort of container to contain this type of temperature. Scientists are still working on it, but right now the maximum time for which we can sustain this reaction is just a few seconds because everything melts and falls apart before it keeps sustaining itself. But maybe one day in the future we will be able to make a certain chamber in which fusion can happen, and we can successfully say that we make energy in the same way that the sun does. That's it for this video. Thank you so much for watching, and do check out the rest of my channel for other physics videos.